In this section, we're going to explore the differences between electron shells, subshells, and orbitals so we can understand how electrons are arranged around a nucleus. Specifically, we'll briefly describe Heisenberg's uncertainty principle before we turn our attention to shells, subshells, orbitals, their sizes, and electron placement. We'll finish our discussion of Heisenberg in a second lecture over this section. Let's begin. Earlier in this chapter, we saw how light can behave as a wave, as evidenced by its ability to bend around objects in a process known as diffraction. Next, we discussed the photoelectric effect, where we saw that small packets of light, or photons, were behaving as particles by causing electrons to be ejected from the surface of a piece of metal when the proper threshold energy was achieved. This was tough to explain, but de Broglie made some progress when he developed an equation that allowed scientists to calculate the wavelength of a moving electron from its mass and velocity, which we'll discuss in the next lecture. De Broglie's contemporaries continued to wrestle with this question, however. 3 years later, Heisenberg was awarded the Nobel Prize for his work elucidating the uncertainty principle, for which he is known. The core tenets of the principle are as follows. The velocity, or speed, of an electron is attributable to its wave-like nature. The position of an electron is attributable to its particle-like nature. However, you can treat the electron as either a wave or a particle, but not both simultaneously. As a result, the more you know about the speed of an electron, the less you can know about its position, and vice versa. On the heels of Heisenberg's award, we see Schrödinger continue this important descriptive work. With the development of the Schrödinger wave equation, we were finally able to discard Bohr's limited model of the atom and move into modern quantum mechanical interpretations of how to find these electrons that are behaving as waves and particles simultaneously. First, we must define the electron orbital as a region of space surrounding the nucleus that can hold, at most, 2 electrons. As you can see from the Wikimedia image at right, orbitals come in different shapes and sizes. It may look complicated now, but we'll describe the shapes and energies thoroughly in the next few slides. Keep in mind that the orbital is the smallest unit of space that we'll use to describe when finding electrons. A subshell is a group of orbitals with the same energy. We label them as S, P, D, or F, depending on how many orbitals they contain. We see that an S subshell contains 1 orbital, a P subshell contains 3 orbitals, a D subshell contains 5 orbitals, and though we won't work with them very much, an F subshell contains 7 orbitals. Once we've grouped our orbitals into subshells, we then organize our subshells by principal energy levels, also known as shells. I typically refer to them as principal energy levels because the numbers n equal 1, 2, 3, etc. correspond to the numbered rows on the periodic table. These numbers are also known as principal quantum numbers. The shell numbers are listed in front of the subshell letter, so that we know exactly which set of subshells we're discussing. While we're discussing these granular details about orbitals, subshells, and shells, keep in mind the general concepts. For instance, lower energy shells will be located closer to the nucleus, which is like holding a heavy textbook close to your chest. It doesn't take as much energy to hold something close. While higher energy shells are farther from the nucleus, which is like holding a heavy textbook farther from your chest. It takes some effort or energy. There's also a general order in that subshells go from the lowest energy S subshell to P, then D, then the F subshell within a shell or principal energy level. Now that you've been bombarded with a ton of information, let's see how we can organize it graphically to make more sense. We have our subshells that can hold 1, 3, 5, or 7 orbitals. Each orbital can hold, at most, 2 electrons. So if we look at the D subshell, for example, we see that it contains 5 orbitals times 2 electrons per orbital to give us a total of 10 electrons for the D subshell type. Does that still seem like an overwhelming amount of information? Now let me show you how to turn the periodic table into the ultimate cheat sheet. The periodic table is arranged in order of increasing atomic number and increasing numbers of electrons. We can think of this area as the S block, and counting columns, we see this S block can only hold 1, 2 electrons. Look at the P block and count the columns. 6 columns corresponds to 6 electrons held in the 3 p orbitals when we place 2 electrons per orbital. Counting columns works for the 10 d block and 14 f block electrons as well. How many electrons can the n equal 1 principal energy level hold, knowing that it only has the 1s subshell? 2 electrons is the correct answer. What about the n equal 2 principal energy level, which contains the 2s and 2p subshells? 8 electrons is correct. 2 in the 2s and 6 in the 2p. What about the n equal 3 principal energy level? Did you get 2 plus 6 plus 10 equals 18 electrons? If not, you may want to work more problems over this material. When we consider the shapes of our subshells, we see that our s subshell contains only one orbital. We call this the s orbital, and it's spherical in shape. The p subshell contains 3 p orbitals, each oriented along a different axis in space, the px, py, and pz orbitals. Each of the p orbitals looks like a dumbbell. The d subshell contains 5 orbitals. 4 of these orbitals look like 4-leaf clovers. The d orbitals have 3 orbitals with lobes, or areas of high electron density, that are located between the axes, the dxy, the dxz, and the dyz orbitals. The 4th d orbital has lobes on the axes, while the 5th d orbital also lies on the axes. Our wave function equation makes it look more like a ballerina standing up on the z-axis wearing a tutu than a typical d orbital. The shapes of the f orbitals become even more exotic and aren't often pictured in general chemistry textbooks, so we won't consider them here either. Each of these orbitals, subshells, and shells exist around an atom's nucleus at the same time, as shown in the picture at right. For example, if we look at the p orbital with the notation 210 in the figure, we would call this a 2p orbital. If we compare it to the 3p orbital to the right, we see the 2p orbital density enclosed in the lobes of the 3p orbital. This proves 2 things. The size of an orbital increases as the principal energy level increases, going from the 2p to the 3p orbital, and the 2 orbitals are indeed overlapping in space. Let's take a look at another image. Here the images of the s and p orbitals are not overlapping, so you can see the relative sizes. You can imagine the 1s orbital nested inside the 2s orbital, which is nested inside the 3s orbital, and so on. The same orbital nesting occurs for the p, d, and f orbitals too, as the principal energy level increases. Which of the following statements are false? We see that A is the correct answer because any subshell can be partially filled with just 2 electrons. If it had said a maximum of 2 electrons, then the statement would be true. This concludes the material for this lecture. As always, here are a few parting thoughts from the textbook authors about this section of information. Please pause the lecture as needed to jot down any notes.